first class lever, I think of like a teeter-totter or a seesaw. And then a class 3 lever is just this, but the effort and resistance are switched. So it's not like flipped over. The arrows are switched. The effort is in the middle, and the resistance is on the outside. Let's see if you understand that. People are typing and like clicking this stuff. It's kind of annoying. I feel like you're not paying attention. So could you stop? Thanks. For this type of lever, you can have a mechanical advantage that's bigger than 1, or less than 1, or equal to 1. Just depends on where you put the fulcrum, the pivot point. Which do you think? I'm going to ask, like, it's going to be a difficult question, but we'll piece it out. Mechanical advantage greater than 1 makes it easier for stuff, right? Mechanical advantage less than 1 makes it harder for stuff. Which one do you think between class 2 and class 3 has a mechanical advantage greater than 1? Meaning it makes it easier. You think it's easier to use the class 3 lever? Yeah? I wish we could try this. Okay, so that door is we can consider it a lever. Yeah? If we want to make it into a class 3 lever, the weight of the door and the resistance and the hinges, that'll be the blue arrow. Okay? If you push on the door over here, is it easier or harder to open the door? Harder. It's harder, right? If you switch the two and you push at the end, it's easier to open, right? So this would have a mechanical advantage greater than or less than 1?
Greater.
Greater than 1, because it would be easier. This would have a mechanical advantage less than 1. For type 2 and 3, that's how it's always going to be. So type 2 is always going to be greater than 1, type 3 is always going to be less than 1. So if you want something that's more accurate, you might want to use class 3 lever. So you can do lots of force with little movement. Or if you want something to be easier, you can use type 2. This explains all of what we just talked about. The mechanical advantage less than 1 on the type 2, or class 2, mechanical advantage. Oh no, sorry, on type 3 they switched it. No, this is all type 1. Never mind. Do you remember what I was saying where you could have it equal to 1 for this is all class 1? If the resistance force and the effort force are equal, you put the fulcrum in the middle, and it has mechanical advantage of 1. So why would you want a mechanical advantage of 1 for class 1 lever? Like it would feel the same way. It would feel the same. You'd have to apply the same amount of effort force with resistance force. Why would you want it equal to 1 though? Anybody think of an idea? No one? Okay, so if I wanted to like lift something up, like I wanted to lift this up, I could have a mechanical advantage. Wait, is it easier to pull something up or is it easier to push something down? Yeah, these would be, mechanical advantage would be equal to 1 because they would be equal here. Yeah.
But I'm saying, would that be the, what you were just asking, would that be the?
Take your time if you think of it later. If I wanted to lift something up, I could use my body weight and then go on the other side of the lever. If I have a mechanical advantage of 1, it would still be easier just because of gravity. Like it's easier for me to apply the same amount of force as my resistance in my effort, but I can apply it in a different direction. This changes the direction of the effort force. So if I want to move something up, I can use a different direction if it's easier for me. Pulleys are actually class 1 levers. We'll talk about that when we get to pulleys, but you change the directions of the effort force. And then moving the fulcrum, if they're equal resistance and effort forces, moving the fulcrum changes mechanical advantage. We'll use us to calculate that stuff. Questions so far? Comments? When I make videos, they'll be a lot quicker, so you'd be advised to pause what just happened. Okay. Second class lever, we talked about this. It's the wheelbarrow. When you have a wheelbarrow, the load is in the middle, and you're lifting up at the end. The wheel is the fulcrum. Always has mechanical advantage, greater than 1. You're using a wheelbarrow, so you can bring a lot of stuff. You can lift a lot of stuff and move it. Oops. So it makes it easier for you. Third class is the forces are switched. So the orientation of the lever doesn't matter. It's still a class 1 and class 2. It matters about the effort force and the resistance force, where they're placed. That's what makes it a different class lever. This one always has mechanical advantage, less than 1. It's like if you had a wheelbarrow and you moved the actual container part of it to the end and you had to pull it from the middle, it'd be a lot harder to do. That's what mechanical advantage being less than 1 is. Moments. So we're going to be calculating some moments in here. The way I think of this is moment or torque. In this case, we'll just consider it interchangeable. It's just a force that wants to produce a rotation or a twist. So we can calculate a moment using the force and the distance between, so like the distance from here to here would be, you would use this distance to calculate a moment using this force. It would have its tendency to rotate about the fulcrum. We'll calculate some stuff. Yeah. So this is one of the equations that you should, or maybe you want to write down, we'll be looking for if you go back through the PowerPoint, to calculate an effort moment. There's an effort moment, so it's tendency to rotate in the direction of the effort force. You use this, and you use the same formula for resistance, you just use the different distance and a different force, because it's a different force for resistance. And also different distance to the fulcrum. So to calculate its tendency to rotate in the direction of the effort force, you have to use the distance between the fulcrum and the effort force and the actual effort force. So you would calculate this moment. So like if force is in pounds and distance is in feet, it would be foot-pounds. Moment would be in foot-pounds. If the moment that you calculate here is equal to the moment that you calculate here, what do you think the lever is going to do if the moments are equal? I mean, this should be intuitive. Okay, let me ask you a different question. If you have the moment here is more than the moment here, what's going to happen to the lever? It's going to tilt which way? Like this way or this way?
That way.
It's going to tilt this way, right? If this moment is greater than this moment, it's going to tilt that way. If this moment is greater than this one, it'll tilt the other way. And I mean, it doesn't matter where the fulcrum is. If they're greater in one direction, then it'll tilt that direction. It just requires a lot more force. If they're equal, what's going to happen to the lever? It's going to balance, right? So that's called static equilibrium. If your lever is in static equilibrium, you have to just set the moments equal, and you can solve for different forces or different distances. Just finishing this calculation, the moment, or the effort moment, would just be 15 times 5.5. This would be in inch pounds, or pound inches. It doesn't, I mean, we'll probably use whatever's convenient. It doesn't really matter. Rotational equilibrium, same idea as static equilibrium. It's just rotational equilibrium is specifically for moments, because it's So if they're in rotational equilibrium, the lever's not moving at all, the moments for either side are equal. That's what it's saying, when the sum of all moments equals 0, that means one of them's a negative moment, one of them's a positive moment. If you set up like a coordinate plane and have a negative distance, or have a negative force, we'll just set them equal for our stuff. So if you knew that this lever wasn't moving, and you knew the force of the resistance, say this is some heavy, some 36 2/3 pound box or something, and you're applying 15 pounds of force on this side, and the lever is staying still, and you already know this distance, you could figure out this distance. Just because if the lever is staying still, you know that the moments have to be equal. So you set the moments equal to each other and solve for that distance. That's what's going to happen here. That's what those calculations are. The moment, the effort moment is this, and we're setting it equal to the resistance moment, but we don't have the distance for the resistance force. And that's what you solve for. So, just doing algebra. Any questions so far? Does anybody need me to go back? No? Okay. If the effort moment, this is like the right-hand rule. I should write this down. I think we'll talk about this again later, but you don't really need it too much now. For moments, the positive direction for moments. Joey, what's up, man? You like the way he looks? That's nice today. For positive direction for rotation is going to be the counterclockwise direction. So this would be positive, and then negative moments would be in the clockwise direction. So I think I just remember it's the same as like when you calculate radians, or you're looking at radians. Positive is counterclockwise. Yeah. So the effort moment would be counterclockwise. That, you would say, is the positive moment, just based on that convention. And then the resistance moment would be clockwise, which would be negative. So that's why when you add them together, they equal 0. Or you can just set them equal to each other and not care about the sign. We'll get more into the sign when we do like cross calculations. Wheels and axles are like levers. You can see if the fulcrum was like a 360-degree pivot point, then it would just be like a wheel. What is this name? Both effort and resistance forces. If unopposed circumference. Okay, we know that. It's the same formula. If you were allowed to go in the entire way around, 2 pi r. I don't know what it's on here. We're not going to use this for today's assignment. So we'll go back to that when we have wheels and axles, or like pulleys. For actual mechanical advantage, I was talking about how it's the actual measured force divided by the effort force, the actual measured effort force. So when it's saying like static equilibrium, or when you need to, I actually don't know if that's part of today's assignment either. At some point you're going to have to say, just assume that the ideal mechanical advantage is the same as the actual mechanical advantage. So like when the question says, what force do you need to overcome static equilibrium, or something like that,